Now I believe your text works out an example very similar to this one, where y of 0 equals 0 and y prime of 0 is 0. Here I'm going to assume y prime of 0 equals v naught. This means we've got our oscillator here, and at time 0 we give it a kick and start it oscillating and see what happens. The solution in the text just says, okay, it's stationary here, and now we're going to start applying this force. So it's going to start it moving a little bit, then a little bit more, etc. Again, we're assuming that delta is less than omega naught. And without going through the details, which we've seen already, we get this as our general solution. And this solution has all the characteristics that we talked about previously. The question then is, how do the initial conditions determine the nature of this transient? The initial conditions are going to determine the values of C1 and C2, which will in turn then determine the nature of the transient behavior of the system. The first condition, y of 0 equals 0, in a very clear and straightforward way tells us that C2 has to be 0. And the reason for that is extremely simple. The sine functions all have arguments that have factors of t, so that they're going to be 0. The cosine also has an argument that has a factor of t, so we're taking the cosine of 0, but the cosine of 0 is 1, whereas the sine of 0 is 0. So the cosine of 0 is 1, and e to the 0 is 1, so that we're just left with C2. And that's got to be equal to y of 0. So y of 0 is C2, y of 0 is 0, C2 is 0. You probably didn't really need me to explain all that. You could have done that yourself, I'm sure. Okay, now, y prime of 0 is v naught. We haven't specified what v naught is, but basically we give this thing a kick to give it some initial velocity. At the same time, we start applying the force. And we do this with the object being at its equilibrium position, y equals 0. Now, if I've done these derivatives correctly and so forth, and you should probably check this to make sure I did it right, but what I come up with is fairly straightforward. The derivative of the sine of, well, first of all, the derivative of this first term has the e to the negative, we're taking the derivative of an exponential function and a sine function. We have to have the product rule. But the derivative of the exponential function is going to be multiplied by the sine function, and t equals 0, that's going to be 0, so we don't have to worry about that part. We just have to worry about the part where we take the derivative of the sine function. We do that, we get the cosine, and we get the factor omega square root of omega squared minus delta squared from the chain rule. T is still 0, so the exponential is going to be 0. So we're just going to get C1 times the square root of omega naught squared minus delta squared times the cosine. T is 0, so the cosine is 1, and therefore the derivative of this part of the function, t equals 0, is just c times this square root. And a similar argument shows us the derivative of the sine omega naught t is omega naught cosine omega naught t. It's going to give us an omega naught in the numerator. We're going to have an omega naught in the denominator. The cosine is going to be evaluated at t equals 0. It's going to give us 1. So we just end up with omega naught times this amplitude out here, giving us this, so that this plus this has to equal v naught. It wasn't really necessary to write these omega naughts here. They go away in this term. We just do a little algebra. C1, we subtract this from both sides and divide both sides by this. We get this term. And this term I chose to write this way, with a single numerator and a single denominator. Then I thought better of it and decided I really wanted to write it this way because it's going to more clearly show the behavior of the system. where we see the effect on C1 of the V naught, the initial velocity we give the object, and the part that's going to be there anyway. Plugging our value for C1 in, and with C2 equal to 0, so this term disappears, we're left with this solution function. Our transient consists only of this first term. It's transient because it has the factor e to the negative delta t, which approaches 0 as t approaches infinity. And this long-term function, long-term behavior, so that long-term the system has an amplitude that's equal to this. The amplitude being greater when delta is smaller and when omega naught is smaller. That's simply because a smaller delta, it means less resistance. That means the system is going to oscillate with a greater amplitude. If there's less resistance, there's less energy being dissipated. And a small omega naught, because if omega naught is large, this sine function goes through its cycle very quickly, which means things are moving very fast. Which means that even if you have a fairly small delta, a fairly small drag coefficient, you're going to lose a lot of energy. And that's going to limit your amplitude. So that we have a very interesting interpretation of this long-term solution. And we can also see